Okay, so we can start a new chapter. Oh, I made a mistake. I said this is 4.1, 4.2, sorry. And chapter 4, and it starts with some introduction of some notions. So this lecture is only basically introducing most of the notions. And then from in the next sections, we will do actually more calculations, really. Although you'll see at the end some. So what are we talking about? Well, let me quickly review what we have done. Remember we had Rn, these were the vectors in n space. So we have encountered the name vector already. So in particular, R square, that was the one that was most familiar to it. We had a plane, and then any point in R square could be thought of as the endpoint of a vector. And then we have a vector here. I denote it this way. Okay? But vectors also, this is how points in R square can be thought in the Cartesian plane, can be thought of as vectors, but we also have seen that we can vector have a beginning and end point where the beginning point is no longer at the origin. Okay? But it's the perspective that we will take is the one that I just have here, is that we put vectors at the origin. So this is an example. R square, R cube, and in general Rn are examples of what we call a vector space. So a vector space. Now, the book gives a rather formal treatment of that. But for our purposes, I'm going to make it much simpler. A vector space is a collection of vectors, kind of a collection of objects that we call vectors. So it's a collection of vectors that, and there's two things we can do, that can be added. We can add the vectors and that can be multiplied by a scalar. Remember, it's just a scalar is just a fancy word for saying a real number. So I remind you what this would be. Of course, in R square, we knew that if we have two vectors, so if this is vector v, then we have the parallelogram rule, that if you make the parallelogram on these two vectors, then the endpoint of the opposite end here, this is the sum. This is u plus v. And that's again a vector. So this is what I mean, we can add them. And we can also take multiples. So remember, if we have u, if you take 2u, would be u twice as, in the same direction as u, but twice as long. So this, for instance, would be 2u. And that's what I mean, we can multiply by a scalar. 2 is a scalar here, but it could be any real number. Now, of course, there are some other conditions here. This addition is like a real addition, like we are used to. This multiplication acts in a way that we can do calculations with. But I'm going to skip the actual definition. If you look at the book, you see there's a couple what they call axioms, certain conditions that is addition and multiplication have to obey. But it's really not something that we want to spend too much time on, because everything that we will deal with it's obvious how we add, and it's going to be obvious how we multiply. So there are, what are examples now of vector spaces other than R square and Rn? Well, in one sense, there are no other examples, and that will be something we'll talk about later. But I'm going to give you a few, but again, the book elaborates much more on them. But I don't want to do that. I'm just going to give you one example that might be a little bit weird for you, but I'll do it nonetheless. Let's look at what I'll call Mn. And these are the n by n square matrices. And I claim they also form a vector space. And so, what does this mean? Well, we have two matrices, A and B, n by n matrices, let's say 2 by 2 matrices if you want to think concrete. Well, I can add them, right? And that's again an n by n matrix, right? We know how to add, that was adding component by component. So let me do this for 2 by 2s. If you have 1, 2, if this is A, 0, 3 say, and B is 4, minus 1, 0, 0, let's take something like that. Then A plus B, how do you do that? Well, you add the first element, you add the second element, that's 1, you add the third element, 0, and these ones, and then these ones, that gives me 3. That's how you add. That's the adding part. And what is about scalar multiplication part, multiplying by a scalar? Well, we know that 3A is the matrix that you obtain by multiplying each of these entries by 3. So 3, 6, 0, 9. And that shows you that it is a vector space. Well, as I said, there are other conditions that have to satisfy, but they are satisfied. So this is a vector space. And there are others. And in fact, in mathematics and in physics, there are a lot of vector spaces do appear. And they are very, they're the foundation of linear algebra, right? Where if you want, linear algebra is really the study of vector spaces. But for us, it will be the study of these very concrete vector spaces that we already talked about in from chapter 3 all the way in the beginning of the class, these kinds. Okay. That's all I want to say about 4.1, although in the textbook there's much more. But more importantly, I want to talk about subspaces, okay? So we have a vector space. So if V is a vector space, now, as I said, for us this will basically mean V is one of these n by n vectors. But I emphasize it doesn't have to be this one, but we will always work in that one. It could be, for instance, this one. But okay, we have a vector space, some vector space, whichever it is, and now we have the notion of a subspace. So what is a subspace? Well, sub, like in subset and so, means it's part of. So it is indeed a subset, and it's moreover a subset that is closed. Well, perhaps it's better if I say it this way. It's a subset. So W is a subspace. So this W is a subspace if it's itself a vector space. Well, you must say, okay, a vector space, don't we have, what is the addition? What is the multiplication? Well, these are the ones that we have from V. Okay? Let me give an example. It's much clearer if I give examples. Let's take R square. The vector space is R square. And let's look now at a line through the origin. So this is a line here, and I claim this line is a subspace. So L is a subspace. Well, what we need to do is we have to check that it is a vector space itself. In other words, we have to check. So what does this mean? Well, it has to be closed under addition. Closed under addition, which we just write plus, and closed under scalar multiplication. That is what it means to be a vector space, right? I remind you, a vector space is where you can add two vectors. So if this W, if this guy is supposed to be a vector space, it means that if you take two elements from it, two vectors in W, and you add them, it should be a vector in W. And it has to be, a vector space has to be closed, it has to have, you must be able to multiply any vector by a scalar, and for W to be a vector space, therefore, if you take any vector in W and you multiply it with a scalar, it should be back in W. So that's what it means, is closed under addition. If you take two elements in W, it's again, the sum is again in W, and closed under scalar multiplication means if you take a vector in W and you multiply it with a scalar, it's again in W. Well, let's look at my subspace here. Okay, what are they? Well, these are points on this one line, and so the vectors here, so here's one vector on the line, and let's do another one. I'll do a different color. So this is different vector, v, and now I have to add them up. So how do you add these things? Well, there are no parallelograms that we can draw here, but remember there are a different way of adding. If you have this whole, in general here, this was one way of adding, but the other way of adding is moving this vector u. You can move a vector and make it this vector here, and then adding is just following the arrows. And that gives me this addition. So let's do it this kind of sum. So in other words, I have to move this VW. I'm going to move this. Let me see what I can erase this. Oh, okay. It's going to be a little bit tricky to. So here was my W. Here's my line. I'm going to draw it a bit as a dotted line, otherwise we get lost. And this was, I'm guessing, a little bit how my W looked like. My V looked like, right? And so the sum now you see is you follow the two arrows, the total thing, so the sum is the red arrow here. This is u plus v. And the result is, again, a point on the line. So, yes, closed under sum. The lines are close to the sum. What about multiples? Well, let's take, what about minus 2 times u? Right? If this is u, what is minus 2 times u? The minus means it's flipped over, and twice means it's twice as long. So we have u once, u twice. So this is how, well, it should be all on the same line, right? So this is minus 2 times u, but it's again on the line, because that's what it is, right? If you take a multiple of a vector, you're in the same direction of that vector. Okay, so a line, therefore, is a subspace of the vector space of R square. Well, a line, but we notice what is important here, it's a line that goes to the origin. What about other lines? Okay, let's look at a line that doesn't go to the origin. So this line here is not a subspace. Well, it's very easy to see. You take just two elements on the line. These are two vectors, right? So this would be this vector u, and this would be the vector v. Where is the sum going to lie? Well, we make this parallelogram. Dear, I'm very bad at drawing, even if it's on a thing like this. So something like that, I hope, right? So here is u plus v. Well, we're no longer on the line. So it's not, because not closed under sum. It's also not closed under multiplication. If I multiply this vector u with, say, 2 or 3, I end up on a vector that lies on this line, but not on the original line. So, conclusion. In R square, lines through the origin are subspaces. And in some sense that they are the only ones. Well, of course, R squared itself is a subspace. It's just everything. And there's another one, a very important one that every vector space has. It's the zero space. The zero space, 0, consists of one single vector. So let's write it in set notation. It has one element only. So it consists just of the 0 vector. And of course, if you take if there's, let's verify that this is a subspace. Well, you have to take 2 elements in it and add them, it should be in there anymore. Well, there's only one element, so okay, you have to take the element twice. If you take the 0 vector and add it to the 0 vector, so 0, this is 0 vector, right? 0 vector plus 0 vector, well, that's the 0 vector. And if you take a multiple of the 0 vector, well, that's also the 0 vector. It's stupid, I know, but it is important. It's an important space, the 0 space, and it's always there, okay? And the whole space, of course, is also always there. So what in our cube, in the three-dimensional space? Well, again, lines to the origin, right? So now in 3 dimensions. So if we have let me redraw this. Sorry. So we have this. If I take any line to the origin, so let's draw a line here to the origin. Perhaps I didn't mean to say it's in the plane, XY plane, so let me redraw this. So perhaps something like that. again, if you look at it, how do you add these elements on this line? Well, it's the same thing, right? You move one vector. If you have a vector here and another one there, and you have to add them, well, you move the first one behind the second one, and you put them together, you're still on the line. So this is a subspace if it's a line to the origin. But there are other ones. Do you see one other one? Bigger ones. Namely, what about planes? Let's take a plane. Okay, I'm very bad at drawing, I told you this. So here is a plane. So we're talking about by this plane here that somehow we have in three-dimensional space. Now let's take 2 points in the plane here. So we have a point here and a point here. So let me try to get rid a little bit of this other thing here that we don't get. Okay. So we have this plane here. Let me get the other axis here that we had. Okay, so we have these two vectors here. This is all in 3 dimensions, right? So you have to imagine this is a 3-dimensional picture. So we have this vector and this vector. Now, how do we add these two vectors? Well, the parallelogram rule says we make a parallelogram. But think about it. Where does this parallelogram live? Both vectors are in the plane. And if you make a parallelogram, well, that's a parallelogram in the plane. So the parallelogram is still in the plane. So this u plus v here is in the same plane. So we see in this, so we had this plane W here. This is a plane. Now it's again important, it's a plane that goes through the origin. Because see, what you want is the whole vector, all these elements lie in this plane, because both the origin and this endpoint are in the plane. And so if I take two vectors like that and add them up, then the endpoint of the sum is again in the plane, so it is closed under addition, and I leave it up to you to verify it's also closed under multiples. Okay, so planes through the origin are also subspaces, and again, if it's not to the origin, then if the plane is not to the origin, it's not closed. So you should try to double check that. Verify the same thing here that I did with a line that is not in the origin. The same is true for a plane not to the origin. I'm not going to draw it because my drawings are getting worse and worse. So let's leave it at that. Okay, so now comes an important notion that is the span. So before I give it the general definition, let's look at this particular example of the plane here. We have these two vectors, this vector u here, I'll draw it again, and the vector v. Both were vectors in the plane. And there's a bit more going on with these two vectors. In this particular choice, well, in fact, you see, it doesn't really matter what I choose. We'll talk about that later. But if you look at these two vectors, okay, the sum is in there. But I could now look at 3u plus 5v. Okay? This is again in the plane. Why? Convince yourself that this is the case. Why? Well, if u is in the plane, if u is in the subspace, then 3u is in the subspace, because any multiple is in the subspace. If v is in the subspace, then 5 times v is in the subspace, because any multiple is in the subspace. So both 3u and 5v in the subspace, so their sum is in the subspace. And you see any linear combination, it doesn't matter the 3 and 5 here, any linear combination. So this is what we call a linear combination. We used this word before, I remind you. So a linear combination of two vectors, or more vectors, is just an expression of this sum of multiples. Okay, so a linear combination is again into this space. So these are all in W, any linear combination. And so we could ask, let's look at all possible linear combinations. So the span of, let me see, I want to use the same notation as the book does, I think. Yeah, span of u and v. That is the collection of all possible linear combinations of u and v. Okay, so we have here a bunch. We have these two u and v's, and we look at all possible linear combinations. So this point, but we can also take twice this and 3 times this, and then add it up. So this would be this point, and so on. What do we get? Well, the answer is we actually, in this example here, so this is an example, in this example we actually get the whole plane. And in general, if you take the span of any collection of vectors, the result will be a subspace. So the first thing is, so let me say in general, if we have a bunch of vectors, u1 up to um, a certain amount of vectors here, let's say they're all vectors inside n vectors, okay, different, this is an m, this is an n, okay, m, n. So they can be the same, but they don't have to be the same. All right, so I take a bunch of vectors in some vector space, in my case Rn, and so the span un is the same, defined the same, the collection of all linear combinations. So linear combination here in general would be a1 u1 bar plus dot 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 plus a m u um underline, where the ai's are real numbers, are scalars. So this is a linear combination, and the collection of all them, that is the span of these vectors. And the claim is this is always a subspace. And in fact, it is the smallest subspace containing the original vectors, containing u1 up to um. That's why it's called span. They are spanned by un, um. Okay? So, and that's going to be a very important notion for us. And we will see that actually every subspace is a span of given vectors, and all that to find out what and how. So we will talk about this in the next sessions. So it's we have to work a little bit on this. Okay, so we have now the notion of subspace, and we have a way of constructing them by taking some vectors and finding the span. So, as I said, we will investigate this in more generality, but I want to now look at a couple of problems that we already can pose. Suppose we are, let's put in R cube. That's a vector space. And look at these two vectors. So I'm now going to a concrete example. Let's look at 1, 2, -1, and V is, oh, what happened here? And V is 6, 4, 2. Okay. So we will eventually find ways of calculating how the span looks like. What is the span of U and V? So if everything that I've been saying is true, there are two things. First of all, the span is a subspace. And we kind of discussed what subspaces in R cube looked like. Well, I gave two examples. I gave you lines to the origin and then planes to the origin. Of course, there is the whole thing itself, and there's also the zero space. And the claim is that we will see shortly is, I mean, in the next lectures or so, is that these are all. There is nothing else. So we have here two vectors here, and the span, therefore, we expect it to be what? A plane, right? So what plane is it? Now, to answer, this is something we're going to, as I said, answer later, but let me now just answer the following question. Let's take a third vector. I'm going to take 9, 2, 7. And the question is W in the span of the other two? Can I at least show what does it mean for W to be in the span? Now, what does it mean? Okay, it means that, so W is in the span. Let me write it just like that. So this means W is in the span of this thing, means that W is a linear combination, A times U plus B times V. Okay, let's write what this means. I'm going to write it out in vectors. So with the coordinates that we have coordinates, right? So this means that 9, 2, 7 is equal to A times 1, 2 minus 1, that's u, plus b times 6, 4, 2. And now let's work it out. Remember, how does it work? We multiply, a multiple of vector is multiplying each of his entries, right? So we multiply a times 1 and then add that 6b. So that's the first element, a times 1 plus 6b. The second element is 2a plus 4b, you see where it comes from. And then the last one is minus a plus 2b. Okay? So this is now the question. Well, so are there a and b? So this, because if it's a linear combination, there must be a and b. So a and b are real numbers, right? But we don't know yet what they are. So the question is, oh, can we find a and b? So what does it mean? Well, we actually have a system of equations, right? We get this system of equation here, 2a plus 4b, and then the last one is 7 equals minus a plus 2b. So the question is, can we find a solution of this system of equations? So some systems of equations have solutions, some don't. And in other words, if we find a solution of this equation, then it shows that W is a linear combination of U and V, and if we cannot find one, then it means it's not. Okay? So we have to solve this system of equation. How do we do that? Well, okay, there are many methods. Let's do it quickly. What's the matrix here of this system of equations? So we look. So a and b are now the variables, right? So the coefficients here are 1, 6, 2, 4, minus 1, 2. By the way, what are they? Well, these are just the vectors. This is just u, right, written in column, and this is just v written in columns. And what I'm saying is, can I find something that is equal to w? Now write w in a column, as a column this is w. And so what I want is an a, b, so that if I multiply, let's get rid of this a here. So that is what I'm looking for, right? An a and b, so that if I take this matrix consisting of these columns times my variables is this column. This is matrix multiplication here, right? And it's all correct, right? So what you have here, a 3 by 2 matrix, this is a 2 by 1, and the result is a 3 by 1. That's exactly how multiplication of matrices goes. Okay, so how do we do this? Well, our method is we have the coefficient matrix, 6, 4, 2, and then we have this augmented by this column 2, 7 here, and we do row operations. I told you, row operations and this row reduction is something that we're going to do throughout the whole course. Okay, so let's do this quickly. I want to make, this is my pivot, obviously, and I'm going to make the first two elements in the column 0. So I do R2 minus 2 times R1. Oh, sorry, let me write it correctly. So R2, replace that by R2 minus 2 times R1, and row replace R3 with row 3 plus row 1. Okay, so that gives me 1, 6, 9 times negative 2, and then add it up, so that's 0. Minus 12 plus 4 is minus 8. Minus 18 plus 2 is minus 16. And now I add, so the second thing I do is, the second row operation is the adding here. So I'm just adding, so I get 0, 8, 16. Okay. This is taking care of this. So now I should want to make a pivot here, but luckily everything is divisible by 8. So I'm going to divide out 8 here. So the row operation that I do technically is replace row 2 by row 2 divided by minus 8. Let's get rid of the minus sign. Okay. So we get 1, 6, 9, 0, 1, 2, 0, 8, 16. And now it's using this pivot, I'm going to make the number 8 below it 0, and the row operation I'm going to do is replace row 3 by row 3 minus 8 times row 2. And what do I get? 1, 6, 9, 0, 1, 2. And so this now becomes 0, 0. Minus 2 minus 8 times 2 is minus 16, plus 16 is 0. And what we see is, we have our echelon form. These are the pivots. And remember, this system is solvable if there is no pivot in this column here. And this is not the case because we have a 0 row here. So we know already this system is solvable. So the answer already is yes. So here we can say yes. Our W, this W here, this W is in the linear combination, is in the span of these two vectors. But now that we're so close, let's try to find out what linear combination is it. Well, this is the echelon form, right? So let's go to the reduced echelon form. And that means that I have to make a 0 there, and there's one more operation that does it for me. I'm going to do row 1, replace that by row 1 minus 6 times row 2. And so I get 1 minus 6 times, that's 0, and now I have to multiply this with negative 6, right? So this negative 12 plus 9 is negative 3, 0, 1, 2, 0, 0, 0, and I can read off my solutions. Remember, the variables were a and b here. So a is negative 3, b is 2. So I can be more concrete. Yes, this is there because we actually have, what are the variables? Minus. So this is actually minus 3 times u plus 2 times v. Of course, once I have the minus 3 and 2, I see it immediately that this is in the span. But the question is to find them. So that's how you can verify that something is in the span or not. So this is testing for spanning. And there will be a couple of homework problems on that. And then one more example, a very important example for us. So example of a subspace. Well, let's take a matrix. And this can be any matrix. It doesn't have to, no, it doesn't have to be. So let A be an, let's make it, I'll try to keep a little bit the same. An m by n matrix, okay? So we have now what we call the solutions. So the matrix, you often get such matrices arise as coefficients of systems of linear equations. So we remember we have a homogeneous system of equations. Means that equal to 0. Right? With the constant vector is all zeros. So the solution set of such a thing. So the solution set of homogeneous system equation, that is also going to be a subspace always. That's the claim. And so why is that? Okay, let's take two solutions. Well, that would mean that's a vector v such that a times v is 0, and it's another vector w, so that a times w is 0. And what I have to show is that v plus w is also in this solution set. Well, let's verify. If it's a solution, then if I multiply with this matrix, I should get 0, right? But I know how to do this. Multiplying matrices is this distributive, so I have this plus that. But this is 0, that's what I said here, and this is 0, that's what I said there. So the whole thing is 0. 0 vectors, I should say, right? Because these are vectors now. Okay, so this shows you that we have a very important, and this is a very important one, subspace that we can get. Any matrix, if you look at it as the coefficients of a homogeneous, and that's I have emphasized this homogeneous system of equations, then you get a subspace. If the system is not homogeneous, actually you don't get a subspace. It's the same thing, okay? So it has to be homogeneous. And there's another way of thinking about this. Remember, we can also think of m by n matrix as the matrix given by associated to a transformation. And how does the transformation work? Well, you took a vector here, So any vector, let's write u here, that was an m vector. So this is, if you want, an m times 1 vector, right? And a is an m times, sorry, yeah, okay, I got it wrong. We have to always be a little bit careful here, right? So it's from n to m, right? It goes the other way around. So we have a vector with n entries. How does the transformation go? Look it up from the section on transformations, and it is just by matrix multiplication. So we have now an m times n matrix that I multiply with this n times 1 vector, and the result is an m. This is an m times 1 matrix, which is exactly an element in here. So that's how this works. Okay, and what we now call the kernel of a transformation, that is by definition all the elements u, all the vectors un, such that the image of u is the 0 vector. So these are all the vectors that are mapped to the 0 vector. Okay, what does that mean? Let's see what that means. Well, what does it mean that the 0 vector, that your u is mapped to the 0 vector? How does this go, this mapping? Well, it's just by product. Oh, so u is in the kernel of TA, and that's written, by the way, let me see here, let me again use a notation. Oh, they have not introduced the notation. Okay, I'll wait with the notation myself then. Okay, so we have u is in the kernel of TA means that this is true. But this means nothing else than saying that u is a solution to the homogeneous system of equations, the one that we just discussed here, right? So this subspace that I taught here, the solution sets of homogeneous system equation, is the same thing as the kernel of the associated matrix TA. So these are just two different ways of looking at the same object. Okay, so the homeworks will be a little bit on. Okay, yes. Let me do one example. Therefore, so let's look at a matrix here. I'm going to take a matrix. Let's take the matrix. I'll take one of the book here. 1, -2, 3. 2, -4, 6, 3, -6, 9. So here's an example of a matrix. It's a 3 by 3 matrix, so we are here. So the transformation that would correspond to it is multiplication by this king. So what's the solution set? Well, how do we find that? Remember, we take our matrix and we try to solve it. But now our column are just zeros because it's a homogeneous system of equations. Okay, I'm thinking of it as in the sense of the original sense that I gave, right? The solutions of a homogeneous system of equations. Okay, so that's it. Row operations, we go again. This is our pivot, so I'm going to do row 2 minus 2 times row 1, row 3, replace that by this guy. Okay, and so what we get, I get 1, -2, 3, 0. -2 times that is 0. -2 times -2 is 4, plus -4 is 0. That's 0. Okay, this of course is always 0. In the back always I'm going to 0. So I don't really need to write it, but I do that for just it's clear what I'm doing there. Okay, so now multiply this with -3 and add up to there. We get 0 again. -3 times -2 is 6. Plus -6, that's 0. I get also 0 there, 0. Oh, okay. So this is an echelon form, right? In fact, is this a reduced echelon form? Yes, it is. Because I have only one row, I have only one pivot, and the condition for a reduced echelon form is everything above the pivot has to be 0, but there's only one, there's nothing to check here. So this also means that I can write down the equation. I know, remember how did it work? We have to look it up again. The non-pivot are the free variables. These were the free variables. and this, the pivot variable, this was a pivot variable, and then what these things tell me is, this means that x1, okay, so I'm going to think of this here as x1, x2, x3, okay, is 0. That's the system of equations that I'm looking at. So x1 is equal to, remember, this means that x1 minus 2 times x2 plus 3 times x3 is 0. But I'm going to solve for x1, so I'm bringing these two guys to the other side. So x1 is 2 times x2 minus 3 times x3. Okay, and this tells me that the space of all elements that satisfy this here, but what is this? Well, this is the equation of a plane. I told you, right? That planes are subspaces, and here we see a plane arising as a subspace, namely as it's the system of the solution set of a system of Euclidean equation, or you can also think of it as the kernel of a transformation. Okay, and even I can do even a little bit better if you think of this. I'm going to just write it here. We'll talk about this more next time. So if I write my vector x1, x2, x3 here, write it out here. Well, in terms of these two guys, well, we have x1 is 2 times x2. So you have an x2 here. Wait, let me write it this way first. So 2 times x2 minus 3 times x3, that's x2, x3. So let's look at everything that has an x2 in it. So, sorry. So we have 2x2, x2 and 0. So what I'm doing is I'm splitting this vector in parts that contain x2 and parts that contain x3. And if there's nothing, then I just write 0. I have minus 3 x3, I have 0 and x3. And now I can factor out an x2 here because they're all multiples of x2. So x2, 2, 1, 0 plus x3 minus 3, 0, 1. What did I do now? I showed that if you take a point on this plane, then it's a linear combination. This is a linear combination, right? With x2 and x3 are the coefficients of this combination of these two vectors. So what I actually showed is that this is the span of the vector 2, 1, 0 and the vector, I write it in columns, minus 3, 0, 1. So not only are system of equations or kernels vector spaces, but I actually find, if I use this method of row reduction, I can find how they are spans. Now, we will go do more of this in the next lecture and study this in more detail. Okay, that's it for today. Don't forget to leave a comment after you've watched this movie.